Hello everyone. So today we are going to see the reagents, which is first level. So in this class we are going to see the paracids. So which is oxidizing reagents, paracids. Generally, paracids means acids which contain peroxy bond. Okay, the bond between the two oxygen, the single bond between the two oxygen is said to be peroxy bond. Okay, so acids which contain peroxy bond are said to be acids. For example, if I consider an acid which is having peroxy bond, so this can be called as acids. Okay, acid. So it is a general form of the acid. Okay, so regular used acids are metachlorobenzoic acid, MCPBA. Okay, so this is what benzoic acid. Okay, if the benzoic acid having a peroxy bond, then it is said to be peroxybenzoic acid. So if it is having chlorine at its meta position, it will be called as metachloroperoxybenzoic acid. Okay, there are many other paracids also available, which are like tertiary butyl paracids. Okay, so ethyl paracid. Okay, so these all are available, but mostly we're going to use metachloroperobenzoic acid as a paracid reagent. Okay, so just a minute. So main application of the paracid is for the epoxidation as well as the Baeyer-Villiger oxidation. So epoxidation of alkane. Okay, so epoxidation of alkane, if you can see, olefin, if it is treated with metachloroperbenzoic acid or any paracid, it's going to give epoxide. This is called epoxidation. Formation of epoxide is called epoxidation. So epoxide is a cis addition. Okay, generally cis addition or same side addition. Okay, so in the same side addition, if you having a cis double bond, this is a cis double bond. Okay, so it's going to give cis epoxide. If it is a trans double bond, it's going to be trans double epoxide. So this phenomena is called stereospecificity. Okay, stereospecificity. So epoxidation is stereospecific. Okay, so if you take a cis double bond or cis olefin, on epoxidation it's going to give cis epoxide. If it is trans olefin, on epoxidation it's going to give trans epoxide. The stereochemistry of the olefin is retained. Okay, olefin is retained. Okay, so during the epoxidation, so what would be the mechanism? Okay, so with the mechanism we can see its reactivity and its selectivity. So it is a very important to know mechanism. Okay, so if I write the mechanism, so what we are taking as a starting material, we are taking starting material as a olefin, and it is treated with paracid. Okay, I am taking generalized paracid. Okay, so this acid acts as a proton donor as well as a nucleophile. So because of the oxygen that is present in distal position, this is called distal oxygen, this is called proximal oxygen. Proximal means near, distal means far. So the oxygen which is near to the carbonyl is less nucleophilic because of the withdrawing nature of the carbonyl. Okay, and this is more nucleophilic because of the less withdrawing nature of the oxygen when compared to carbonyl. So this is more nucleophilic, so this is going to attack on the olefin. Okay, and at the same time it's going to attack back. Okay, or if you take stepwise, so initially attack of the oxygen to the olefin, then this bond is going to migrate here. Generally it will happen within a single step, not in two steps. So this will become plus. Okay, so this is going to happen, and this minus whatever is there is going to attack on this, so H plus will be going to eliminate. Okay, or if I write even more explanatively, so initially if it is a H plus is eliminating. Okay, so it's going to give this an attack of the oxygen, so estate will be going to eliminate to give epoxide as well as the acetate ion. So this acetate ion will be going to abstract the proton which is already left during the reaction to give acid. So from the per acid, final outcome will be acid as well as the epoxide. Okay, so during the attack, so if it is oxygen attached to this side, the again attack of the anion on the oxygen will be with the same side. So that's why stereochemistry is going to retain. Okay, or if it is cis attack will be cis epoxide is going to form. If it is trans epoxide is going to form. Okay, so now we have seen the stereochemistry. Now if it is more steel, if more than one double bond is there and their steericness is different, let's say example is this. So if this is the condition, generally more substituted olefin or this is called electron rich olefin. Okay, the more is the electron rich, the more will be the going to attack of the oxygen onto the double bond is going to happen. So wherever the more nucleophilic olefin is there, their epoxide formation is going to happen. So this double bond is more nucleophilic, so here it is going to form epoxide. So stereochemistry will be from the downside, as if you consider these two metals are above the plane, so oxygen attack will be going to form below the plane. Okay, so stereochemistry will be written because it is a planar one. The paracid must attack from the any of the side because it is a planar. So whatever the side it is going to attacking, that will be reversed to the methyl, because if you consider methyl is above and it is attacking from the below, this would is the product. If I consider methyls are below and oxygen attack will be above the plane, its opposite will be the product. If you rotate again, it's going to form. Okay, so this is about the stericness and stereospecificity with the examples. Okay, now one more stereochemical approach. If it is cyclic or bicyclic starting materials and epoxide formation is going to happen with the per acid. So oxygen supply from the per acid will be always from the less steric side. So as I informed earlier, so the downside of this bicyclic compound will be more steric when compared to upper side. Okay, so oxygen attacking will be from the upper side, so it's going to give exo product majorly, where the attachment is above the plane, that is said to be exo, where the attachment is below the plane, that is said to be endo. So in this condition, exo will be the major. Okay, if this is tertiary butyl group. Okay, so if the condition is like this, and you going to treat it with perbenzoic acid. Okay, perbenzoic acid in the same solvent, chloroform. Then what could be the product? Write the product and submit through the WhatsApp. Okay, so we'll see some more examples. So if it is more than one double bond is there, so what could be the criteria? So the criteria is more the electron rich double bond is there, that will be going to attack more often. Okay, so epoxidation is more probable with the more steric or more electron rich olefin. So out of these three, which olefin is more steric? The more methyl group substituted will be more steric. Okay, so if you want to solve the problem on your own, just pause the video and solve on your own, then see what could be the product, whether you have capable of depicting the proper product or not. Okay, by pausing the video you can write down on your own, then you can see. Okay, so here the more substituted will be the epoxide formation double bond. The product will be this one. So the starting material is said to be beta myrcene. Okay, so beta myrcene, it is a natural product. Okay, so this question is repeated in HU. Okay, in previous questions. Next. If the substrate is like this, so wherever the alcohol groups are there, okay, then what could be the product? So as we are using acid, acid, okay, so there is a probability of hydrogen bonding, formation of hydrogen bonding with alcohol to the oxygen. So if this is the case, or there is another possibility of hydrogen bonding to the carbonyl. Okay, so if the carbonyl is attached and this is free, okay, so it will be attacking from the same side, which is OH is available, because hydrogen bonding is developed between the hydrogen of the OH as well as the carbonyl. So the attacking of the oxygen will be going to happen to the same side. So the resulting of epoxide will be to the same side. Okay, so this will be the product. The reason is hydrogen bonding. So this is very important reaction, asked many times in the previous papers. So next example. So next application. So far we have seen the oxidation of the olefins. Now we are going to see the oxidation of the amines. So oxidation of amines is very specific. So it depends on the amine type. If it is tertiary amine, this is a tertiary amine. Okay, If it is a tertiary amine on treatment with paracid, it will be going to convert into tertiary amine oxide. Okay, tertiary amine oxide. From the tertiary amine on paracid treatment, it's going to give tertiary amine oxide. If the condition is with primary amine, okay, with the paracid, okay, primary amine, so the amine group will be turned into the nitro, okay. So this is one of the best way to convert the amine group into nitro, okay, simple oxidation of the amine to nitro. So the reduction you can use lithium aluminum hydride and sodium chloride and other reducing agents also, okay. For the conversion, for the oxidation, you can use paracids. Okay. Next, if it is aromatic heterocyclics of nitrogen, okay, aromatic heterocyclics of the nitrogen. This is also a kind of unsubstituted hydrogen, unsubstituted nitrogen. Okay, there is no hydrogens attached to the nitrogen. So if this is the condition, then N-oxide formation is going to happen. Okay, N-oxide formation is going to happen with the paracid treatment. Okay, next. So in the next application, we are going to see the oxidation of thioethers or sulfides. So oxidation of sulfides. So if you take sulfide or thioether on treatment with metachloroperbenzoic acid, it will be going to convert into the sulfoxide. Okay, sulfoxide. The same reaction we have seen using manganese dioxide. Okay, MnO2 and manganese acetate also. Okay, so same it is a substitute for the manganese reagents. Okay, so if you use metachloroperbenzoic acid, sulfides will be converted into the sulfoxide. If the sulfoxide is present, if you treated with metachloroperbenzoic acid, it's going to form sulfone. Okay, sulfones. So this is sulfoxide, this is sulfide, this is sulfone. Okay. If it is a sulfur heterocyclic compound on trifluoroperoxyestic acid, okay. So the structure of trifluoroperoxyestic acid is this. Okay. So if the trifluoroperoxyestic acid is there, so it's going to give directly sulfone. Okay, direct sulfone. If it is sulfur heterocyclic compound. Okay, these are the specific examples which are repeated in the previous questions. Okay, in various examinations. Okay, so that's all for oxidation of the paracids. Okay, thank you. And you need to work out the given example and send by the WhatsApp. Okay, thank you.